Hi, we're going to go through some projectile motion examples. So let's say I take that initial velocity, 52 meters per second, and I put it on a raised platform 5 meters off the ground. And I shoot that thing horizontally. You might think of this as maybe a bow and arrow type example. You're tree stand hunting with a bow, you shoot straight out 52 meters per second. How far could you go? How long would it be in the air? Those types of questions. Alright, so let's tackle how long is it in the air. And I'm going to want the y dimension. And so my v naught in the y dimension in this case is 0. My acceleration is positive, so 9.8 meters per second squared. And the time is what I'm looking for, and that's basically the fall. This is fairly simple to set up. I have my change in y is equal to v naught yt plus 1/2 at squared, where my change in y is positive, my v naught in the y dimension is 0, and so I can solve for t fairly easily. And so this becomes 2 times 5 divided by 9.8 square root equal to t, which is 1.01 seconds, is basically how long it's going to fall in the y dimension. Remember that this velocity has no bearing on how long it's in the air. So for distance, I'm going to look at the end point here. And so if I lay out my variables again, my delta x in the x is what I'm looking for. My air time is 1.01 seconds as previously found, and my v in the x is the 52 meters per second that we originally saw. So again, solving for delta x is going to be vt equals delta x, which is 52 times 1.01, which is a little bit further than 52 meters. Okay, now we're going to do another example. This one is basically just a vertical launch. So we're going to take out a lot of the x dimension pieces. We'll go do this in a lab, but I'm going to shoot an object straight up. It's going to come to a velocity of 0 as it changes direction momentarily, and then it's going to come right back down. And essentially everything on the way up is going to be equal to everything on the way down. I would like the total amount of air time and how high it will go. Okay. So I'm going to start with t up, and then I'm going to multiply it by 2. So I had an initial velocity of 52 meters per second up. My velocity at the top was 0, and so because I chose the velocity at the top being 0, that turns this t into just that halfway point t, or the t up. A is negative 9.8 meters per second squared because that initial velocity was positive. So everything has to jive. When I do some basic algebra, I come up with 5.3 seconds, that's t up. I know the symmetry of up equal down, and so if it took me 5.3 seconds to go up, it's going to take me 5.3 seconds to go down, and so my total air time will be 10.6 seconds. Now to solve for the height, the maximum height here, this is the h max. My initial velocity is still 52 meters per second, and I was using it for 10.6 seconds. Oh, I'm sorry. I don't want to use the total airtime. I want the top height, so I'm going to use a half airtime. And that's what kind of sometimes can get confusing here. So I want that 5.3 seconds, the half airtime, plus negative 9.8, and then the 5.3 seconds squared again. So when I do all that math, I'll get 137, 138 meters for the maximum height. What would happen if I changed my launch angle to 45? So now I'm going to do this, where this theta is equal to 45 degrees. My launch is still 52 meters per second. How far would it go? Well, we understand that the amount of time that the velocity in the x dimension can work is equal to the amount of time that it's in the air, which is directly related to its y-dimensional components. And so I'm going to start with the y-dimension initial velocity and find my total air time, and then I'll use my total air time and that initial x dimension velocity and multiply that through. Alright, so using the y dimension at the end, I can find the total time. So when I use my y dimension at the end point, I understand the launch velocity is the same as the impact velocity, and so the y dimension component here is the same as the y dimension component here. It's just in a different direction. My 9.8 meters per second squared going down holds true, and that'll give me the total amount of time in the air. And so when I use my final velocity equals initial plus AT formula, so the second kinematic equation, it will give me a total air time of 7.5 seconds. Now that I know that it's been in the air for 7.5 seconds, I can use that and the x component velocity to solve for distance. So 275.92 meters. There are a couple things that we recognize here. We saw that the total air time at a 45-degree angle is 7.5 seconds. The total air time at a 90-degree angle is 10.6 seconds. So there's some rules here that we can pull out of this example of a vertical launch and a 45-degree launch. The maximum amount of height and the maximum amount of air time come from a steep launch angle. The maximum distance that you can get comes from a 45-degree angle, because if I dropped below a 45-degree angle, I would eat into this air time even more, and I would have trajectories that would end up falling shorter and shorter and shorter. But the same thing happens if I start going higher and higher and higher. These start matching up. So I trade air time for velocities. So the optimum distance is right here in the middle, right? 45-degree angle launch. A diver leaps from a cliff 30 meters above the surface of the water. He leaves with 2 meters per second velocity and a 40-degree angle above the horizontal. Question A, what is the time to the water? Okay, so V naught y is equal to V naught sine of theta, in this case 2 sine 40 degrees, which is going to be equal to 1.29 meters per second. Now if I say that the final velocity is 0, I can find the V in the y is equal to V naught y plus AT. V y is 0, and v naught y was at 1.29 meters per second that I just found, and then a is going to be negative 9.8, and so I have vy minus v naught y over a, which is equal to my t up, and you want to be careful about your labels here. And so when I plug in this information, I have 0 minus 1.29 over negative 9.8 t up, which is equal to a very small 0.135 seconds, and we'll use that later. Okay, now keeping in mind that I need to know how much higher I'm going, plug in my initial y, so I'm starting at the origin here, plus v naught yt, which is going to be that 1.29, and then my time 0.135 plus 1/2 negative 9.8, and then again 0.135 squared. Once all that's plugged into your calculator, it will spit out 0.09 meters, and that is my maximum height. The next portion here, I'm going to do my final y change with an initial y naught, and now my y naught is actually the y max, and you keep in mind this is a negative 30 because of my reference point, so I have to have 0. I'm starting above 0, and I'm going to go to 0 and then go past it. So the way that we're going to plug this in, I'm going to end up at negative 30, but I'm starting at 0.09 above my initial velocity in the y dimension. Because I'm starting at the top, the v here was 0, so this term goes away, and I'm left with my 1/2 negative 9.8, and then the t squared. The t is what I'm looking for. And so if we do some algebra, and that was the t of the fall. And so I originally asked what was t total, which is going to be t up plus t fall, which was 0.135 plus 2.48, which will end up being 2.61 seconds is the total air time. What will happen to the diver in the horizontal? I am looking for the delta x and the x, and I already know that my time is 2.61 seconds. Delta x is what I'm looking for, and the v naught and the x is the velocity that's going to carry me through. This math is a little bit nicer to us in the x dimension because I just have my v equals delta x over delta t, and I'm looking for delta x, and so I have vt is equal to delta x, and my velocity was 1.53 for 2.61 seconds, which gives me about 4 meters of travel in the x dimension. Same scenario. What is his impact velocity and his impact angle? So we're going to look at the other side of this problem. V sub y is going to be equal to, now we recognize that these are components, and that in order to find the v impact, I'm going to need to use Pythagorean's theorem, where vx squared plus vy squared, take the square root of that and you'll get your velocity as my final impact velocity. So if I blow this part here up a little bit and draw a different picture, I've got my velocity here, and I've got my v sub x and my v sub y, and the angle that I'm looking at, if this was the water here, right, is the angle to the nearest horizontal. And so because the v sub y is in the opposite position and the v sub x is in the adjacent position, I can use the tangent of v sub y over v sub x. And when I plug those numbers in, 86.4 degrees. even though that this number is a negative value, it really doesn't affect the angle because the angle kind of is only going off from the magnitude of the leg there. And so I can ignore that negative value for the sake of finding my angle. Okay, we have horizontal launches. You're going to need to be able to solve for time, the height, and the distance, given a certain amount of information. Typically, you need to start in the y dimension and finish in the x dimension. Total height, air time, this could be T-toe or T-up. Typically you're not asked to solve for the delta x. They might ask you for the impact velocity, and so this is almost all in the y dimension. You could be asked to solve anything from total air time to the height to the distance. This is going to be a combination of y and x, so I would start in the y, finish in the x, but these are the more complicated versions, and so you may need to do pieces in both as you move along. This one's challenging to give you a rule about how to tackle it. Cliff questions, and there's a couple of them. You could drop an object off a cliff and it'd be all in free fall in the y dimension. Launch an object down, same thing, it's just you have where v naught is 0 here, v naught is not 0 here, it's going to be a positive number. And then you also have the up and then the down, so where you have a initial velocity in the y, right? Free fall, which is the initial velocity in the y is 0, everything's in the y dimension, and then this is still all y dimension, but your v naught is not 0. And then this one, you have a range of things. You could do total air time, you could do max height, you could do max distance, you could do impact velocity, lots of different things you could ask about this one. So this is kind of all of the projectile motion problems all in one spot. And you should be able to do horizontal launches, vertical launches, angle launches, and then the different types of cliff launches. Okay? So we're going to go through a lot of practice of these in class. We'll do a couple lab with these as well.